Hello everyone, this problem is asked in GATE 2022 and it is of 2 marks. It is of 2 marks. And this problem is from the electromagnetic field theory subject. So let us see what the question says. It says that as shown in the figure below, two concentric conducting a spherical shell centered at r is equal to 0 and having radii r is equal to c and r is equal to d are maintained at potential such that VR at R is equal to C is V1 and VR at R is equal to D is V2. Assume that VR depend only on R, where R is the radial distance. The expression for VR in the region between R is equal to C and R is equal to D is. So for detailed description and for detailed concept about the Poisson and Laplace equation, kindly refer this NPTEL course Electromagnetic Theory by Professor D.K. Ghosh, Department of Physics, IIT Bombay. And the YouTube link for this course is given here. Now let us see some basics regarding this question and then we will solve the problem. So as we all know that there are three orthogonal coordinate system we study in electromagnetic field theory, and these are Cartesian. First is Cartesian coordinate system having orthogonal axis as x, y, z, which having infinitesimal distance, a small distance dl, and volume can be written like this. And for cylindrical coordinate system having orthogonal axis as rho phi z, and inf- uh, cylindrical coordinate system infinitesimal small distance dl and dv is written like this. And now for a spherical coordinate system that is having coordinate axis as r theta phi, and for this infinitesimal small distance dl and dv is written like this. And we are having four different types of operator we study in the EMFT theory. Having first one is the only delta that denotes gradient, and delta with dot product that denotes divergence, and delta with cross product with any function that denotes curl, and del square that denotes Laplacian. Now let us see what is Poisson's and Laplace equations. So Poisson equations states that the Laplacian of the electric potential is equal to the volume charge density divided by the permittivity with a change of sign. That means del square V is equal to minus rho V divided by epsilon. Now if in a region where there are no charges, that means rho V is equal to 0. Hence we can say that this equation becomes the converted Poisson equation is converted to Laplace equation, and Laplace equation is del square V is equal to 0. So first one is the this one is the Laplace equation, and this one is the sorry this one is the Poisson's equation. Poisson's equation, and this is Laplace equation. So what is the statement of Laplace equation? Laplace equation states that the Laplacian of the electric potential field is zero in a source free region. Like Poisson's equation, Laplace equations combined with the relevant boundary conditions can be solved for VR, but only in regions that contains no charge. Alright, so we are going to use this concept to solve this problem. Now, how we can find the Laplace of any function, any function? So first we will write generalized form of a orthogonal coordinate system, and then we find the Laplacian. We have to find this Laplacian of any function. So Laplacian of this generalized orthogonal coordinate system we can write like this: del square V 1 divided by h1 h2 h3 and so on. Now for the spherical coordinate system, we correlate with a generalized uh, coordinate system. So here h1 becomes 1 and h2 become r and h3 become r sin theta. Now we'll put all these h1, h2, h3 in generalized expression. We will get this del square v for this lower one. We get this for a spherical coordinate system. Now let us see the problem. So solution for this problem is, we know that Laplacian of function is given like this for a spherical coordinate system, since this question having a spherical coordinate system. So since here we have, it is given in the problem is that since VR depends depends only on R, therefore therefore del square V therefore del square V therefore del square V we can write like that, because this second and third term become 0. So 1 divided by r square sine theta into del dr r square sine theta 1 dvr dr. So this is equal to 0. From the Laplace equation. So we can say that on simplifying this will become r square dv dr is equal to a, where a is constant, where a is constant. Now we have to find the generalized expression for VR. So now we, we can write like this: dv divided by dr is equal to a divided by r square. Therefore, on integrating both sides, you will get VR is equal to minus AR plus B. So this is the generalized expression for electric potential, and we can be called it as 1, where B is constant. Now using the boundary conditions, so we have seen here using boundary conditions, using boundary conditions. So at R is equal to C, V is equal to V1. Therefore, V1, here you write better VR. VR is equal to V1. So V1 becomes minus A divided by C plus B. So this is 2. Now at r is equal to d, using the second boundary condition, at r is equal to d, Vr is equal given as V2, so it becomes V2 is equal to minus A divided by D plus B. So this is second expression. On second and third, on subtracting second with third, you will get V1 minus V2 is equal to minus A divided by C plus A divided by D. So again we write V1 minus V2 is equal to A C minus D divided by CD. So it becomes A is equal to V1 minus V2 C minus D CD, right? So from second we can find the B value. So we got here the constant term A. From second we will get the V value. Now putting this A in second, so we have seen that V is equal to V1 plus A divided by C. So B becomes V1 plus V minus V2 C minus D CD. So this we got B. Now putting both these constant term in the generalized expression for electric potential, that is first expression, putting A and B in first. So what we will get? Then we will get VR is equal to minus V1 V2. So it's a little space. So VR is equal to minus V1 V2 C minus D CT divided by R plus V1 plus D V1 minus V2 divided by C minus D. So on solving this, you will get final expression like this. So I can write one more step. So V1 minus V2 CD divided by D minus C R. So minus we coming here. So V1 D minus V1 C minus V1 D plus V2 D divided by D minus C. So final expression we will get VR is equal to CD V minus V2 divided by D minus CR plus V1D get cancelled out. So V2D minus V1C divided by D minus C. This with the final expression for electric potential at in the region between R is equal to C and R is equal to D. So now we are going to match with the options given here. So we can see that correct option is B. Thank you.